Okay. Just getting that up. And we're back. X squared takes 7x take 18. 9 and 2. X take 9 times x at 2. P squared take 5, p take 14. P takes 7 times p at 2. M squared take 9, m at 8. M take 8 times m take 1. X squared takes 16x at 63. 9 and 7. Seven x squared take 31x take 20. 7x there in the first spot. And we need to make 31 somehow. Oh, 5 and 4. Take 35, take 35x at 4x. Yeah. Factor out k. That gives you 7k at 9. That's really all you can do. Okay, 7. Okay. Take 7 at 4. Here. 2b in the first spot. 3 and 7. Here. 5p in the first spot. Take 2 and then add 9 there. Factor out 4n squared. So we have 7n squared plus 4n. Take 20. And try to go further with that. 7n. Two and 10. There. Factor out b. 3b squared. Take 5b. Add 2. Try to go further with this. And take 2, add 1. 7x. Hmm. 3 and 20 won't work to get 21 and 20, or 140 and 2. 4 and 15. Well, that would make 105 and 4, or 28 and 15, so that won't work. 5 and 12. Well, that would make 35 and 12, or 84 and 5. 6 and 10. 70 and 6, or 42 and 10. So it's this one. It's this one. Take away 6 of them and then add 10 of them. There, like that. And for this one here, factor out 3. So we have 10n squared b take 29nb plus 10b. Oh, and b. Like this. And then put that in there. You know what? 5 squared at 4 squared makes 29. So try this. Like that. And for this one here, open brackets. We could try 3r. And then take 15 at 6, but that doesn't work. Take 30 at 3, doesn't work either. Let's try again. Okay, just try 9. And try 2 and 5. You know what? Try the discriminant. $385, which is not a perfect square number, so this actually can't be factorized over the integers. This has no integer factorization. Like, it will have a general factorization like this. And in this case, because the discriminant is positive, it'll be one of those surd expressions, but you can't find an integer factorization. So for here, 73 is a prime number. So bring out r. So we have 9p squared. That's 73p, that's 70. And just for fun, try the discriminant again. B squared minus 4ac. B is 73, and 73 times 73 is 5,329. And take away 4 times 9 times 70. So 36 times 7 is 2520. And 2520 taken away from 5329 is 2329 plus 480. So that's 2729, which is 2,809. And 2,809 is a perfect square. It's the square of 53. And so that means a factorization of this thing does exist. So we just have to find it. So there's going to be 2 plus signs here and here, because we've got a positive coefficient there and there. And we need to make 73. So we could try 3 first of all. And then 1 and 70, no. 2 and 35. No, that won't work, because it would be 3 times them added together, and you would never get 73. So it must be 9 and 1. That's awesome. Okay. Now, two and 35. Doesn't work. 5 and 14. 5 and 14. Doesn't work. 7 and 10. It does work. So 7 there, 10 there. Okay. I'm actually enjoying using the discriminant on here. 49. 36 times 56. 2016, I think. Let's see. 201620592065. So I don't think factorization exists, because that's not a perfect square. The squares, 40 squared is 1,600. 50 squared is 2,500. 45 squared is 2,025. And that's the closest that you can get. So we'll check. Okay. Not factorable, not factorizable. Those are equivalent. Here, x on the outside, 4x squared at 43x at 30. Just apply the discriminant just for good arithmetic practice, why not? So 43 squared, 1849. Take away 4 times 4 times 30. And 16 times 30 is 480. 1849, take away 480 is 1449. And then that becomes 1369. And for the squares there, so it's going to be under 30. So about 37, let's check 37 squared. That's 900 plus 420 plus 49. So that's 37 squared, so it is factorizable, or factorable, as they appear to say. So I could put 2x there. 2x there just to begin with. And many combinations to check through. But I don't have to do this, because when I do this, I'm assuming that they will add up to an even number, which they don't. So better is checking 4. I absolutely love it that I saw that. So 1 and 30, 2 and 15, 3 and 10. And I believe that's it. And then here, we'll do the discriminant one last time, just for fun. Because I need to practice my squares. 89 squared. So that's 64 at 144, 784, 7921. Take away 4 times 10 times -9. So that's 7921 plus 360, which is 8,281, which is 91 squared. So this has a factorization. So let's find it. Now, if I add 9 and take 1, it seems to work. For what values of b is the expression x squared at bx at 12 factorable? Okay, so we could just run the possibilities. So x at 1 times x at 12, x at 2 times x at 6, and x at 3 times x at 4. This gives 13, 8, and 7. Name 4 values of b which make the expression factorable. So like x at a times x, no. It's positive on the end. But they haven't said anything about b, the b has to be positive. Just that they have to sort of like and when you do this, so a at c equals -3, and there's so many possibilities here. Like let's just try 1 and -4. And when you do this, it implies that b is -4. And then let's try 2 and -5. And when you do this, that implies that b is -10. 3 and -6, making b -18. And clearly you can see an arithmetic sequence on the right. No, wrong. Sorry, beg your pardon. Let's try this. -28. Some possibilities there. Some possibilities there. Some possibilities there. Okay. Save. And move on. Next up, we have solving equations by factoring. Okay.